Okay, this is problem 4.4 in the book. First thing you got to do is the loads. What about the dead load? What is it?
24.
Okay, how'd you get that?
0.7 times
0.7 times 1.2, 0.84 kips per foot. What about the live load?
1.9 times 1.6 was 3.04.
3.04. Okay, what about the self weight? How big's the beam?
15 base.
15 times what?
28.
Divided by 144 times 0.15 kips per cubic foot times
1.2.
1.2 because it's a dead load.
0.525.
We'll call it 0.53. You add up all those, and what do you get?
4.41.
4.41 kips per foot. That's the uniform load. There is that dead concentrated load, which you still have to multiply by 1.2 because it's, service load. So that comes out to be 9.6 kips. Yes?
You put in 15 times 28. I
Yeah.
thought it was B times D.
B times H.
Uh,
Self weight goes all the way down to the bottom. All right? So, my shear diagram is based on a beam. How long is this beam? 30, so 15 foot. I got a uniform load, 4.41 kips per foot, half the beam. This is still going to be a symmetrical beam, okay? And then I do have that 9.6 kip concentrated load at 5 feet out. So what does my reaction come out to be?
I did. It's 75.75.
75.75? We got agreement on that? Okay, so then your shear diagram, again, half of it runs out to 15 feet, goes up to 75.75. It goes down 5 feet at 4.41 kips, so 4.41 kips per foot times 5 feet, you subtract that from 75, what do you get?
53.7.
53.7, then you hit the 9.6 concentrated load, and that drops you down to what?
44.1.
44.1, and then over the next 10 feet, you go down 4.41, so you go down to 0. So that's basically what the shear factor shear diagram looks like. First thing we probably want to do if we're looking at a design for this, or even an evaluation, is to think about what is my critical shear, because you got to beat the critical shear. So the critical shear occurs a distance D out from the face. Do we know what D is?
25.4.
So let's think 25.4 inches out is, still inside this first 5 foot section. So we'll do this. VU critical, the way that we have in the past. We are going down 4.41 kips per foot. The X distance is D, 25.4 inches out. I'll change that into feet, and I'm starting out at 75.75. So my VU critical value comes out to be what?
66.42.
About 66.4 kips. So that's really what I gotta beat. So all this other stuff is good, but my VU critical is sort of what I gotta beat. Now this is an evaluation problem, but again, I mean, you gotta evaluate it based on what VU critical is. Okay? So, this problem says, hey, I got a number, different spaces. I got one space at 2 inches, that's a locator, that's not really a spacing. Okay, so we don't have to evaluate that. I've got 5 spaces at 8 inches, and then 4 spaces at 10, 8 spaces at 12. So, basically, what I would do is this. You got, like I said, a number of different spaces, 8-inch, 10-inch, 12-inch. So we may as well figure out what the design capacity is for each one of those. So 8 inches. We know what phi is. What is V sub C? What's f prime, 2 square root of f prime c? What's f prime c? 4,000. B is 15, D is 25.4. Divide that by 1,000 just because I'm working in chips.
48.2.
Say it again, please.
48.2.
48.2 kips. V sub s, when I'm at 8 inches, AV is, I guess a number 3 star.
Yeah.
Okay. So 2 times 0.11 times 60 KSI times D times 8 inches. $41.9. So phi VN at this 8-inch spacing is 0.75 times 48.2 plus 41.9.
Or 67.6.
So, at an 8-inch spacing, which is basically where I start out at, I've got a design capacity of 67.6. As long as I maintain that, you can see I'm above VU critical, so I work. And I maintain that for how many inches out? No. 42 inches. 1 at 2, 5 at 8. 5 times 8, 40, plus 2, 42. So, again, if you're doing this on graph paper, you could really see it. I mean, you could say, hey, 42 inches out, that's, 3.5 feet, blah, 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 and you could see that that's it. What happens at 42 inches out?
Start spacing at 10 inches.
You start spacing at 10 inches. So what do you got to do? You got to do the same thing. You got to figure out now, and this gets sort of easy from this point onward because this is the same, that's the same. The only thing that changes is your spacing here. So that changes V sub s. And then when V sub s changes, of course, design capacity changes. So at 10-inch spacing, what do you come up with?
61.2.
61.3.
No, I was thinking
Total 61.3. What's V sub?
33.5.
V sub S is 33.5. Now your design capacity is 61.3. So really now, when I come out and I start the 10-inch spacing, I really just have to confirm that at 42 inches out, that my diagram here, my VU diagram, is less than or equal to 61.3 kips. How am I going to do that? Straight line formula. Whereas 61.3 located, my line's going down 4.41 inches, or kips per foot. I'm looking for how far out that this happens. Okay, and I'm starting out at 75.
3.3.
So X is equal to 3.3 feet, and in inches that is
39.3.
39.3 inches. So this value of where 61.3 happens is really closer. It's in here someplace. It's not, it's not, I'm dropping down at 42 inches, but I could have dropped down at 39.3 inches. So I'm past that point. So I'm good. I'm actually, out here and dropping down. Okay? So I've made the drop at an appropriate place. All right? Where do you go onward from here?
12.
Yeah, as long as I'm at a 10-inch spacing, I'm at good, but a 10-inch spacing does end someplace, and it ends when it changes to a 12-inch spacing. So you'd have to go through, figure out what your design capacity is at 12 inches, and then check to see if it's at an appropriate place.